We'll get started. Okay, let's pick up where we left off. Let's see if I can chase that away. Screen sharing, thank you. There we go. Okay, so we looked at two of our, actually, let me start with logistics. So the exam grades for exam 2 are out, regrades are open. So if you have anything where you think your answer better matches one of the other rubric options, do let us know. I'll talk more at the end of this lecture about some other things I'm going to do, because mean with medium were a little lower than I was hoping for, so I am going to adjust some of the assignments going forward. Okay, so we finished off looking at VI and MSI as a pair of coherence protocols. There are lots of possible coherence protocols. We're only going to look at one more, right? MESI. And let me give you a caveat. The types of coherence protocols that we are looking at are all things that would work well in the small, right? So these are all snooping protocols. We're all assuming buses. If you looked at the simulation of coherence protocol that we did on Friday in recitation, right? You obviously saw that everyone just saw everything at once. It's all atomic broadcast. If you're looking at how this plays out and why we still keep coming up with new coherence protocols to this day, buses don't actually scale too well, so do keep that in mind. But you can make versions of all of the things you've seen work on more complicated network topologies like meshes using directories and so forth. If you find that interesting, take 530. We're going to stop at snooping bus-based in this class. So we'll go on to MESI. Okay, so in the same way that going from VI to MSI allowed a program behavior to be better optimized, right? So VI to MSI said actually some of our data is read shared. So I don't need to go and invalidate it and have a Highlander rule of there can be only one, or things which are all identical copies, right? So read sharing is fine. MESI is likewise going to take MSI and support a common behavior pattern, which is that some data is globally read shared, some data is globally read write, and some data is just mine, right? I am the only thread that's actually going to access this data. So the assumption in MSI is when I do a read of data, it must be globally shared. That's my first default assumption. I'm from invalid to S on a read. In MESI, I make the assumption that if possible, I'd like to get my own copy of this, so an exclusive clean copy. It's our new state that we're gonna pull out from there. So if I go and contact, again, snooping bus-based protocol, I say, I want a copy of this. I'm going to do a load miss. And it's the response I get from the other parties is that no one else has a copy, right? Then I'm going to go into the exclusive state. And what's going to be different about the exclusive state is that I'm going to be able to make this transition to modified without a write upgrade miss, right? So if I know I have the only copy, clean as it may be, in the entire system, I don't need to tell anyone that I'm going to modify it because there's no one else to invalidate. I'm going to be able to remove one of my bus transactions in the common case of I read some variable I, that is my variable I increment variable I, no one else needs to be told about this, right? We're good. Okay, so we've gone from 2 states to 3 states to 4 states. And each of these is filling a different pattern. Now, if that data really was shared, right? So if other ones do have copies, we're going to do the same pattern we saw in MSI. All right, so if I go and put a load miss out there and someone else says, yeah, I got a copy of that, here, you can have one. Right, so you have to change the protocol a bit to acknowledge the fact that now these other parties are responsible for saying something if they actually have something in the shared state. We'll get to that in the next slide. Then we're just going to do the shared state same as before. Right? If it really was read shared data, we'll end up in the same state that we were in MSI, no worse. Right? In the common pattern where I have some of my own data where I read it and then write it, right? Again, we get benefits here. If I'm just streaming out a bunch of data, is MESI going to give me any benefits over MSI? I'm just writing a new data structure, right? I'm just computing some output stream, filling in some, maybe I'm zeroing out some big matrix. Never been touched before. Is MSI or MESI going to behave any differently based on this state transition diagram? I'm initially invalid, doing a bunch of writes. No, they're exactly the same, right? The only new behavior for MESI over MSI is the case where I have a load miss and the rest of the system responds that no one else has a copy and you get exclusive privilege, and I can do the E to M transition silently without global notification. Excuse me. Okay, so here is the state transition view of it. Right. So you're looking at the local behavior, right? So on a load, I'm going to go to S or E, depending on the response I get from the memory about why it's providing me with this data. Right. So that's going to basically be the difference here. Right, so when the memory, as the provider of last resort, provides it, it has to actually have enough information to tell you that there were no other copies around. You can look at this column here. It looks the same as in MSI. The store behavior is pretty much identical, except obviously we have a new row here. Right, so now this is a hit instead of an upgrade miss. So relatively minor modification, but now we've seen 3 variants. Any questions about the MSI to MESI transition and what we're trying to achieve? Right? Again, we're capturing a particular program pattern. Right? So MSI captured read sharing in a way that VI did not. MESI captures private data accesses, private read-write data in a pattern that MSI does not. Okay. Okay, and as I said on Tuesday, we've end of life Kahoot. So let's just go over some what would have been a clicker question here. Okay, so now that you've seen these 3, I want you to think about what it would mean for them to be better than each other. I think about the design choices among these coherence protocols. Okay. So based on what I've said so far about these 3 protocols, is it going to be A, right? MESI is strictly an improvement over MSI, which is strictly an improvement over VI? Is it that these 2 are cool because they have more letters and VI is just old? Or is it that MESI and VI can sometimes outperform MSI, and that MSI and MESI will outperform VI on particular cases? Right? Which of these things are going to be true? So think about why we had these different protocols. Right? And the answer was because there were particular program patterns we wanted to enable. If you do not have that pattern, right, there is no particular benefit to that coherence protocol, right? So if all I'm doing is actually having my own private data and then occasionally a synchronization, right? VI is fine, right? There is no sharing other than a synchronization variable, which is going to be read-write between multiple things anyway. And in particular, because you don't have any upgrade misses in VI, VI can actually outperform MSI for some workloads. All right, so MSI is going to assume on load that it's shared. If everything is actually private, VI will actually be better than MSI, fewer bus transactions. MESI and MSI are actually a little more strictly ordered. Right? There isn't actually a case to be made that MSI is going to have fewer transactions than MESI. It may have the same. So the only argument between those two is one of complexity. But what this will ultimately mean is depending on your program pattern, right, the relative benefits of these can be differently ordered. Okay, so both C and D are actually true. All right, so MESI and VI, because they handle private read-write data just fine, perform MSI. They don't make an assumption of sharing if the sharing isn't there. Right, don't pay an overhead. Both of these will be better than VI if you have any read sharing, because VI does not support read sharing. Right? So this is not a strongly ordered set. Right? That is what I want you to take away from this. Okay, so how does this all matter when we map it back to performance, right? And other data transfer overheads that we're concerned with, we're looking at our cache design or multiprocessor system. So this is basically the fourth type of C, right? So we have our traditional three Cs of compulsory, capacity, and conflict. Our fourth C is coherence, right? So if you're basically asking, why did I get a cache miss? Right? You have the three original reasons, and then the fourth is someone else kicked it out of my cache. Right? So all of these things we've been looking at are write and validate protocols. So every time that someone goes and decides to do some writing, right, your copy may mysteriously disappear. Okay? Now, how big is it? It's not enormous, but it's visible here. So if you look at these graphs, this red part here is the impact of coherence misses. You'll note that depending on the application and the scale, this is the number of cores that are running. The more parallelization that you have, the larger the number of coherence misses that you're actually getting as they become more complex synchronization. Right? So it's not nearly as big as your other three Cs, but it does need to be taken into account. Now, let me give you one other thing that you need to understand when you see these sorts of graphs for parallel programs. You're looking at a measurement of programs that have already been optimized to run on parallel platforms. Right? So if you took this and did this naively, I guarantee you could get arbitrarily large fractions of that bar red. Right? Well-optimized parallel programs do as little talking to each other as possible because talking to each other is expensive and painful. Right? So coherence is necessary for the correctness of the program, but we spend a lot of time in optimization trying to engage with coherence as little as humanly possible. So do keep that in mind when you see any of these values here for parallel benchmarks. And if you want to look at some particularly pathological cases of where a lot of time gets spent in coherence misses, there's a good study from late 90s in some of the SGI, the old big graphics rendering machines, where they found that 30% of the time in some of these programs was actually spent getting uncontested locks, right? Just because going through the memory system to do the atomic primitives that are needed to get your own exclusive copy of things. So, at any rate, your mileage may vary, but it is something to take into account. Okay, the other thing you have to keep in mind is that when we talk about patterns like read sharing, we don't actually operate in our cache on variables, we operate on blocks, right? So your processors don't arrange to share a variable X, they share a particular physical address, right, in a region of some size, say 64 or 32 bytes. And so all of the invalidations, all of these operations in the coherence protocol have been happening at block level. So what if I have variable A and variable B living in the same block? Let's say that core 1 only ever manipulates variable A, core 2 only ever manipulates variable B. Well, there's still going to be a problem, right? Because my protocol is operating at block level. This is an example of what we call false sharing, right? So if I have reads and writes to elements of a block that never actually communicate data between each other, but are manipulating the same block, right? I'm still going to feel potentially really nasty coherence effects, right? I mean, again, imagine that, again, fire your compiler writer if your I++ in your loop is living in memory instead of register, but imagine that your I++ in one loop over here is in A, and this is your I++ in some other loop. These are getting updated all the time. All right, this could be arbitrarily ping-ponging back and forth between these two caches every iteration, right? Be very, very bad. If they're both read-only and you have MSI or MESI, you'll just get 2 copies. But as soon as you have any write behavior, right, on either of these, right? So let's say A is read-only, but B is read-write. This whole situation is going to be very, very slow. Right? Okay. Now, if you look at the way that we tend to parallelize programs, and we will see, it's not in this deck, it's in the next deck, we'll see some examples of parallelization with OpenMP. The effects like this, false sharing, are one of the reasons why you don't see usually fine-grained allocation of data to threads. Instead, you get big chunks. So if I have a big array, right, A equals 0 to 1 million, right, array A, million elements, and I've got 8 threads, right? I chop this array up into 8s. I do not do every, mod 8 elements, right? I would get nasty, nasty false sharing. All right, so you chop it up. If you get the alignment right, you get no false sharing. Worst case, your million elements, 8 threads, you just have 1 piece of false sharing at the boundary of each of these partitions. So the way that things are laid out in memory can be very important in understanding the coherence effects that you actually have. So again, if you go back to here, these have been laid out well, right? So if you had a bad layout, those coherence misses would go up quite a bit. Okay, so let's just see if we understood false sharing. Let's look at a few examples here. Okay. So if A and B are 2 distinct variables in the same cache line, which of these patterns would see additional misses due to false sharing? Think about the different cases. I got thread 0, thread 1. Let's walk through each of these cases. So first, for A, is this false sharing or actual sharing? It's actual sharing. They're both reading A, right? A is actually a shared variable, right? Okay, how about B? That's false sharing, right? Okay. Okay, write A, write B, read A, actual sharing. Read A, write B, write A, read B. Again, these are actually shared. Read A, write A, read B, write B, false sharing again. Right? Now, if we look at the ones where there is actually false sharing, right? So B and E, which of these are going to experience more misses? Which of these is the false sharing causing a fundamental problem in the MESI protocol? So again, read sharing in MESI is fine, right? Protocol supports this. This, however, is going to be problematic. As soon as you get writes into the equation, you're going to cause invalidations. Right? So here I have a read and a write to A, a read and a write to B. Right? Whatever order that comes in, right, I'm going to invalidate the other copy, even though there's no actual data sharing that's occurring. I'm going to cause an additional coherence miss due to an invalidation for one or the other of these here. Okay. And now imagine this not at one level cache line, right? Across lots of cache lines within some loop. And you can see why false sharing could be particularly pernicious. The other place that false sharing is very problematic. We're not going to really cover that in this class, but it's interesting if you want to read up on it. How many people are familiar with the transactional memory extensions that Intel released about a decade ago? Nobody? Okay. So it turns out that transactional memory and false sharing are natural enemies. If you're ever interested in thinking about how many people have taken the databases class? Also, one of you. Okay, so let's not talk about transactions then. But suffice it to say, false sharing and transactions are also very problematic in practice. Right? 'Cause it'll cause unnecessary aborts. Okay, so great. So we have lots of options. Coherence is there for correctness. It's important that you get it not completely wrong with the patterns of access that you actually have, or that little red bar is going to go very high. And with that, we now have an ability for the hardware to ensure that there can be an agreement on what the value of a particular memory address is at cache block level. Now, this, however, is not enough for your entire programming model to work in a parallel execution environment. You also need to consider consistency. So coherence is being able to agree that, address 5000 has a value. Memory consistency, and this is something that's going to be defined at the ISA level, right? So this is exactly how your memory coherence works. Purely a hardware feature. This is microarchitecture, right? If I took your MESI and swapped it out with MSI, you'd see a performance change, but you wouldn't have to rewrite your programs. If I change your consistency model, you need a new ISA. Right? So this is actually going to be baked into the definition of what correct execution even can be. This is going to be about an agreement on whether address 5000 or whether address 6000 was updated first, right? And while being able to at least agree that a given location has a value is kind of important if you want to build any sort of shared data program, it will turn out, unsurprisingly, that in a parallel program, understanding something about the order of events is also really important, right? So again, think about your bank account. It would be nice to agree, right, that your paycheck was deposited before your rent check was, cashed, right? It would also be useful to have agreement from all parties involved that those happened in the same order and not have mutually distinct ideas about which order those happened in, leading to complaints all around. So those sorts of questions are about memory consistency. Right? So why do we care about memory consistency? Why do we care about order? Right? This is really going to be about understanding updates that are used to order other events. Right? So if we're in a shared memory machine, right, the way we communicate data is with a set of stores. Right? The way that we know that something has happened is with some set of stores. Right? So how do I actually know about the set of all events that have happened based on some message I'm writing into memory relative to the other things that comprise the data that I actually want to be visible? Okay. So first, let's define what we mean by scene. So think about your interface between your processor and the memory system. We're going to assume, without discussing it further, that all the things we're talking about are coherent memory systems. So when we present something to the cache, it is then going to become visible. Right? And what we are going to want from any of our models of memory consistency is some flavor of write serialization. Right? So that's the notion that a store is not fully done until it has been presented to the coherent memory system. Right? So when your store is still sitting in its store buffer, it's not really done yet, has not interacted with the rest of the multiprocessor system or anything about store completion. in the sense that it actually has talked to the cache. So we're going to assume that your program order is always valid. Right? We're not looking at something like a Tomasulo-based machine, which didn't actually have strong ordering guarantees and other weird non-precise exceptions. So this is normal, right? So nothing new here happening other than the fact that we're going to talk about presenting this to the rest of the system. Where before we didn't really care about that when we had one core, right? As soon as in the store buffer, we knew it was going to get taken care of eventually. Now we're going to start worrying about when did everyone else actually have any possibility of seeing this, right? Because the other cores can't see into your store buffer, right? The caches keep each other coherent, right? The caches are going to broadcast this information and get the values updated, but it has to actually leave the store buffer. Okay. Now, what you're going to think about, especially when you think about the out-of-order execution that's happening, is the relative order of loads and stores. Right? So if you have a model where really only one of your cores is doing something every sort of logical time unit, then sure, there's nothing to worry about. Right? But in practice, between every one of these bus transactions, between when these things are actually being drained, you may have done internally some number of loads. So are those loads going to see the value that everyone else sees? Are those orders all going to agree? This is where consistency gets fun. Okay, so let's look at a few different models. So the strongest model that you're going to see in anyone actually talking about is sequential consistency. Okay. So sequential consistency, it means that your program is going to look like the threading was a series of interleaved executions on an old mainframe. Right? That's one way of looking at it. There is some sequence of interleavings of the executions of all of the parallel components, right, which would have produced the same result that everyone observed. Okay. So the basic ordering properties are going to be there, right? So cores see their own loads and stores in program order. Great, right? Even in our out-of-order execution already does this. We're going to see everyone else's loads and stores appear to have occurred in their program order. That's not actually naturally enforced by something like coherence. And finally, all of the cores are going to agree on a viable partial order, right, among these loads and stores. Right? So if you have all of these things true, I'm going to argue this is going to be indistinguishable from an interleaving of a multi-program uniprocessor. It's very easy to reason about. There are all sorts of things you can do in sequential consistency, but it turns out from a hardware perspective, there are a bunch of things you can't do. Right? Getting that global agreement is not terribly performance friendly. Right? So if you have an x86-based machine, you do not have sequential consistency. Because again, I told you this is an ISA-based property. x86 has what is known as total store order or processor consistency. Okay? So we can delay things arbitrarily in this model in the store buffer. We don't have to immediately present them to the cache and get everything synced up so that everyone sees the stores happening in the same order. Right? So everyone will see these stores from every processor in the order that they occurred, but it's not going to say anything about the relative ordering of the loads to those stores. Okay? So we put things in the store buffer, and some of my loads can see those stores well in advance of when other people can see those stores. And what this is going to give you, right, is a different set of partial ordered dependencies than you might get in sequential consistency. This is still a relatively strong consistency model. Right? A lot of things that you think are normal will still happen. I'll give you an example in just another slide. But you can actually prove with as few as 3 participants that these are not identical, that there are cases that this allows, that this does not, with the load and store interleaving. And then finally, for all of your phones, this is one of the reasons why certain notables used to joke that ARM stands for arbitrarily ridiculous machines. Again, they may have been funded heavily by Intel. But ARM has what's known as release consistency. So this is a very weak model. So you can drain things from the store buffer in any order. Right? So you're not even guaranteed that the observation of writes into memory that you see matches that seen by any other particular processor. And so the way that you're going to look at your programs working across these platforms, right? And this is one of the challenges with portability of code, right? Also, one of the reasons why you should use the existing synchronization libraries and not write your own, right? Is that these models are in fact different. The ISAs will allow, you don't need it in sequential consistency, but you need them in processor release, a variety of what are known as memory fences, right? So you can force some ordering properties by draining the store buffer and doing internal ordering between your own loads and stores and when they become externally visible to emulate stronger consistency models on weaker consistency models with some additional work and some additional performance penalties where necessary, right? And that where necessary part is why you have these different models. So again, imagine that I am not actually talking to any other thread. Think about much of the history of ARM. One core, embedded processor, whatever, right? I do not want to sacrifice any performance, any efficiency. I just want this thing to work as simply as possible. If you want to do any multiprocessing, programmer can go fix it. Compiler can fix it. Someone can insert a bunch of M-fences, right? And give me my ordering back. Right? So some different assumptions. Okay, so let's make this a little more concrete. Right? To understand why consistency matters. Let's just say that a long time ago, A was 0 and flag was set to 0. Right? So in the before times, all was 0. Then on core 0, we're going to execute these two instructions, A equals 1, flag equals 1. Core 1 is going to run this code here, while not flag, do nothing. And then once flag becomes 1, print A. Okay. So if I tell you nothing about what machine we implemented this on, what does core 1 print? So think about the different models, right? So if this is on a sequentially consistent machine, I can interleave these 4 lines. Yes, I'm actually interleaving them at a finer granularity. They're not actual C lines, but without loss of generality, right? This is basically a read of flag. These are a pair of writes. Think of this as a read of A. Print is actually an amazingly complicated function. Let's not think about it too much. Right? Value could actually change in the middle of printing. Let's not worry about it. Okay, but imagine that I'm just interleaving these 4 lines, right? So sequential means that there's going to be some interleaving that whatever my output is equivalent to, right? And so under that, if you think about the various different interleavings, right, there is no interleaving where I can get to printing A before everyone has agreed that flag has been set to 1. Right, so if I'm just interleaving these on some single unit processor, executing some instructions from one, some instructions from the other, right, under sequential consistency, the only possible thing I can get is I'm going to print 1, right, because A is set to 1 before flag is set. What about total store order? Total store order is also going to be strong enough because total store order says whatever I observe over here on core 1, I don't know about the load ordering, but I'm going to observe the stores occurring in the same order that they did on core 0. So total store order means that over here I will see A equal 1 before flag equal 1. I don't know when I'm going to see it. I can't tell you anything about what core 0 was reading from these and what order that saw. But I know that A1 will be observable before flag equal 1. It's still a relatively strong ordering. We're still going to get, A equals 1. What about a release consistency? What's it going to print? It's still well defined, right? There are a finite number of possibilities it could print. Could it print 3? No, right? Right, it's only going to print 0 or 1, but we don't know which one, right? It doesn't actually give us any guarantee, right? Release consistency doesn't tell us whether it's going to print 0 or 1 with the code that's given, right? So now you can begin to see why programmers of multi-threaded and parallel applications care a little bit about the consistency model. So I would like to know, right, that I've actually finished writing my data before I tell you I wrote my data, or whatever flag is representing that I want you to actually do. I want to know that I'm in a consistent state before I do it, right? That's a pretty basic property in your shared memory machine, and yet you can get some complications. And as I said, even with an example with only three threads, you can even come up with situations where total store ordering is not as strong as sequential. Right? It's a bit contrived, but you can still get it. Okay, so coherence says nothing about this because it's not a coherence problem. Right? Coherence just says that A has a value and flag has a value, right? And so the worst thing that happens, imagine you're running this on an ARM machine with release consistency, and sometimes it works and sometimes it doesn't. I will tell you this is the worst possible type of bug you could have. Right? This is just 1 bit. Now expand this. You got branches off of a bit that is either 0 or 1 that have branches off of a bit that is either 0 or 1. Right? Your space can be very, very large. And again, the other place that this is going to come up, right? If you're running on a dedicated platform, you're doing all of your code on ARM, you know this is a problem, and you fixed it. So talking to people in industry who are doing code review for massively heterogeneous deployments that have to run on everything, and they got a brand newly minted, PhD student who thinks they're really clever and has never bothered to actually check that their code works on anything other than their own development environment, and they have to get a little wake-up call about, there's a reason we don't write our own synchronization primitives, even if you think it's much faster, right? Okay, so let's do this just in terms of store buffers to get an idea here, right? Boop. So there's an example of where you would actually get this behavior in your release consistency. Okay, just to drive it home, right? Where 0 writes to A, misses in the cache, puts A in the store buffer, keeps going, writes 1 to flag, writes it directly into memory. Right, this is how you can get the reordering from a reasonable hardware perspective. Right, again, ARM did not decide to do this for no reason. Right, enabling this sort of behavior is a performance optimization for the 1 core. Just makes it painful for the synchronization. Now, again, even in your parallel program, that's probably fine to pay some additional burden of throwing in a bunch of fences to restore this behavior, because most of the time in your parallel program, as I just told you, if it's a well-designed parallel program, you aren't actually talking to the other threads. Right? So if I'm writing my own variable in its own cache line, you're writing your own variable in your own cache line, I don't care what order these were observable to the memory system. Right? If there is no actual sharing of data, right, the ordering doesn't actually matter. Right? So you can buy back this synchronization properties of order if and when you actually need them for some overhead. Okay, we're not going to talk too much about particular fence options. You can have sort of a global fence that just drains the store buffer and halts all of your memory operations until you've done so. You can also have things that just do that for loads or just do that for stores. If you're interested in that, go take a compiler class. Okay, so we've gotten how they're talking to each other, how they're going to coordinate through understanding that the values actually have the variables actually have common values. They can get some agreement on the ordering, but we're not quite done, right? because it will turn out that unless you have a sequentially consistent model, you need a little help if you want to do a number of common interaction patterns, like a lock. Okay. So let's look at some common interaction patterns. This is fork join, right? So I want to have a point in time at which I dispatch a bunch of, again, this is from the current Wikipedia OpenMP documentation. I haven't changed the language yet to, I think they're called managers and workers now. Right? It'll be fine until our next unionization push. But a single point in time that everyone can agree happened, release a bunch of threads, those run in parallel or concurrently. There's a single point in time at which we can agree that everything is done, fork join, right? This is called a barrier, right? A point of common agreement among all parties in a program. You will get finer grained things like locks, semaphores. There's a whole variety of flavors. But if you're doing something like OpenMP, fork join is actually pretty common. And let's look at why, when you are trying to synchronize agreements about time, A, that it's difficult, and B, why hardware is going to want to help you, right? We want some help from hardware. So the right way of thinking about this is when you are dealing with a multiprocessor, you are in distributed systems land. All right, you are in the land of partially ordered sets rather than linearization of time. Right, so think about your classic operating systems, distributed systems timeline diagram. Right, I've got some set of events. Some are local, right? Some are communicated. Time goes that way, right? So if these are a set of timelines on some process A, B, C, and E, and you look at these various events, order them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's give you a couple more. 13 and 14. There is no linear order among all those 14 points. A partially ordered set, right? Does 1, 2, 3, or 4 come first? Any relative ordering of that is legal from this dependence graph. Yes? Very closely related, yeah. So the nomenclature is very similar, but the things that you're worried about because of the granularity and the mechanisms by which they're occurring look a little different. And in particular, the cost of enforcing some of these properties. So the cost of getting effectively consensus on a chip multiprocessor and a distributed system are radically different. In no small part because all of the protocols that these work on assume no failure. So if you have no failure and time-bounded delivery, and then some of the protocols aren't as miserably expensive as, like, Paxos. Yeah. Yep. Yep. Yeah. So we're coordinating through different cores on a shared memory machine. So the other issue that you have in most distributed systems don't assume that it's a shared memory device. So they're communicating through explicit messages. So that looks a little bit more like the MPI model rather than like an OpenMP model. But the consistency models are basically the same. Okay. It's just that if you have message passing, you're looking at consistency among messages received rather than memory itself, because memory isn't shared in a distributed system. Okay. But so here's your standard timeline diagram. So you get concurrency and you get partial ordered sets. So right, keep that in the back of your mind. Your notion of time stopped being linear when we went to parallel programs. We went to parallel hardware. right? We do not get a linearization where everything strictly comes before the next thing. We still have causality, right? 1 comes before 5, 5 comes before 6, right? 5 comes before 7, right? Messages are sent before they're received, these sorts of things. But we don't have that relationship defined across all pairs. It's only a partially ordered set. Okay, so that's the world we're living in. And in that world, we'd like some help from hardware for some of the things that we would like to do. Okay. So imagine that I've got the following attempt to build a spin lock. Let's start with how many people are familiar with spin locks? Okay, so let's back it up a bit. How many people have heard the term critical section? Mutex. Okay, so mutex stands for mutual exclusion. So it turns out that one of the things you want when you are doing parallel programming is to be able to have a section where you know that only one of your various actors is acting, right? Let's say I have a bunch of attempts to concurrently modify your bank account. They're going to happen in some order. How are we going to impose order? We're going to only let one of these actions to your bank account occur at a time. Everyone else has to wait, right? Particulars of how they wait, don't worry about it. Reader-writer locks, etc. But mutual exclusion is your friend, right? So we want to be able to have a property that only one thing is active. That's a critical section, right? So a spin lock is a simple way of acquiring access to a critical section. It works kind of like it says on the tin. I'm going to keep asking for access to the critical section until I get it. If I don't get it, I'm going to loop and try to access it again, right? It's just a polling routine for access to a lock, right? Okay. So if we look at this here, so I set my lock variable to 1, right? I load the current value of my lock variable. I check if it is currently unlocked. If so, I check again. If it is unlocked, I lock it, and then I do all my protected stuff, and then I set it to 0. Okay. So is this going to work? Leading question, obviously not, otherwise I wouldn't be asking a question about it. Right? It's not that it will never work. Right? If it would never work, that would be easy. Right? No, this is one of those sometimes problems. Right? So it's not A. Right? It's not B either, because if the other thing is in fact locked, it will spin, not continue going. Coherence does not fix this. Coherence just allows you to even agree what the value of L was at a single point in time. And the problem here is you're not dealing with a single point in time, because here I loaded it. Here I locked it. How far apart are these in time? How far apart are these in time in terms of events on other things in the parallel system? Unknown, arbitrary, right? Right? I could get interrupted by the operating system here, rescheduled next month, right? It's not a great way of assuming how that's going to work, right? So sadly, D. E doesn't actually cover this case, although it turns out you can, although it is a much more complicated locking approach, bakery locks. You can actually build a lock that will work with just loads and stores in a sequentially consistent memory model. Go read Leslie Lamport's paper on it if you're interested. Otherwise, the lock code it's a lot. Very inefficient. You don't want that. So while it is technically possible, not with this code, to do this on E, you want hardware to give you the ability to do something about this time gap, right? I need to have an atomic operation. Right? I need to have the ability to both read and write without being interrupted, right? Because I want to conditionally lock, right? If it's already locked, I don't want to be locking it myself because it's already locked. I don't have access to it. But if it was unlocked and I locked it, I don't want anyone else to be interrupting me between when I realized it was unlocked and when I locked it. Right? So hardware is going to give you some primitives to do that. Okay. Again, if you want to see this play out visually, it would basically look like this, right? Here are two codes, both of them attempting to acquire the lock, right? So initially, this value is 0. I see a load miss, or one does a send data and validates its copy. Right, now we both have copies here at 0. That one is invalid. You store goes to 1. Right, this one is going to come on out. Boop. But there's a problem, right? Because we loaded it, when we loaded it with 0. Now we're storing it again, and it's going to go back to 1. We both think that we've locked it. Right? This is not going to work. Okay. So if you want mutual exclusion, you want semaphores, you want all these other nice properties, you're going to ask hardware for some help. Right? Now the good news is, in this bus-based system, there's an obvious single point of serialization where you can agree on ordering globally, namely who got access to the bus. Right? If you're looking at a more modern complex system, say a directory-based system, for any particular address, there will still be a single point of serialization in the system for all paths to that address, even if there is no global point of synchronization in the entire system. So wherever your lock variable lives, right, I guarantee in any system there will be some point in the system that everyone will have to pass through to get to it. So all these things are going to be built on top of that. Okay. So it turns out that there are enormous families of different hardware primitives that you could have to help you with this. Right? So they range from the very simple test and set, right, which checks if a value is 0 and then sets it to 1 if it's 0. Otherwise, just returns the original value. To compare and swap, which is a more complex version of that. Load lock and store conditional, which is what we're going to talk about here, right, which is effectively a one cache line transaction. Right, so a conditional update to a line depending on the state that the loaded line is in. Right, we're going to basically piggyback on top of coherence. There's a whole family of what are called fetch and fee. Right, so fetch and add, fetch and increment, fetch and something, which return the value, current value, and modify it in some particular way. The fetch and fee types tend to compose. So if I have two different fetch and adds, I actually can compose both of those together. So if I'm doing atomic increment, I don't actually have to have only one succeed, because I know how to combine 2 plus 1s together and return some intermediate result. So if you're looking at old school multiprocessors with multiple sockets with custom network logic between them, a common model was that the network logic might support fetch and fee, where you could actually get combining of these multiple operations in network in transit. A little less common now, although the primitives around there are still there if you've ever played around with built-ins. There are built-ins for mapping fetch and increment and such to x86. But compare and swap, load lock store conditional. As a brief aside, compare and swap is generally preferred over load lock store conditional because it has fewer pathologies. But LLSC is the pair that's in MIPS, and so it's the one we'll talk about here. Okay. So let me check the times. I do want to do logistics at the end. Lots of time. Okay. Okay. So how are we going to fix our problem of reading at one point in time and writing at another? Right. So I've mentioned that there are some primitives that just, as a single primitive, do both. Those tend to be a little complicated, and traditionally they were implemented at the memory controller. So you basically push everything out to some point deeper out in your coherence network where there's only one serialization point. You do all the operations at the serialization point, and then life is fine, except that those operations are very slow. They're not very cache friendly. The way that MIPS and RISC-V and the PowerPC and a number of other things have done it is with a pair of instructions So we're still going to have this gap between these two operations, but the second one is going to have behavior conditional on the coherent state of the first. Right? So again, let's think about the logic of this. I don't need to know that nothing happened between my load and my store. I only need to know that nothing happened that could have modified the value that I loaded. Right? So I don't need this to happen atomically. I need the value result to be equivalent to this having happened atomically. It's a transaction, right? And so if you think about how coherence can do this for you, right? So if I acquire a version of this cache line and I have received no coherence traffic about it, right? Then I know that the value that I read is still valid, right? This is going to be a sufficient condition. Okay. Now, I'm going to need to link this store conditional to that LL, right? So I need to set some particular state. So when I do this load, right, it looks just like a load word, except I'm going to set some other internal microarchitectural state that says, by the way, track the coherence for this line. And if anything happens to it, or if it gets evicted from the cache, if I lose any certainty about this, say that it's unsafe, right? So this falls out of cache, unsafe. I don't know what the value is anymore. Right? It gets invalidated. I definitely don't know what the value is anymore. I get a coherence request that modifies its coherence state. No, not safe. Right? Again, I can share it. That's fine. The value hasn't changed. Right? So you can set your policy depending on what your coherence policy is. But this is basically going to integrate with your coherence policy, right, such that any possible value change to this is going to invalidate the bit that determines whether this store conditional succeeds. Okay. So now your store conditional is going to do two things, right? If you know that this loaded value is still valid, store succeeds, acts just like a store, and returns. The only difference is it overwrites this R1 with a success code, because since it can fail, I need to check it. Right? Store conditional can fail. Store conditional could say, I didn't do a store, so you need to go try again. Handle it in software. Right? So R1 is going to be the success code. So a little bit of overhead in that this gets blown away. You have to keep writing the value back again if you need to try again. Right? These are not going to nest in most of these architectures. You could imagine a version that has some number of different link registers. Stop that imagining right now. It's probably not worth it. Right? You're not going to do load lock store conditionals within load lock store conditionals. It's not clear which one you're pointing to. It's like, no. There's one link, one outstanding store conditional. We're just going to set this one bit. Very simple. If you want lots and lots of these in parallel, go use those transactional memory extensions from 10 years ago that I told you about. Go learn that TXM. Okay. So now I mentioned that if this leaves the cache, right, or other things happen, that this will be invalid. So this is, again, this is very simple, and it cache piggybacks, and it's cache friendly, but you can live lock. You can write code that will never succeed. So imagine the following. I have an n-way associative cache. I load this value. I then do a series of operations that all go to the same set and kick out the value I just loaded. And then I try to store conditional. It'll just never succeed. It'll just loop. Your code will loop indefinitely. If there's a page fault between here and here, it's going to fail. If there is an interrupt between here and here, it's going to fail. Right? So it's very conservative. So you can get live lock problems with LLSC. But in practice, they're like 2 or 3 instructions between these, and you don't worry about it. Right? So if I'm going to do load, add 1, store, I'm going to be okay. Right. Anyone have any questions on why it is sufficient to track whether or not modifications have occurred to this line for the store to succeed, even though these don't actually happen atomically, and an arbitrary amount of other stuff might have happened in between them? Okay, cool. Okay, so what's that thing going to look like? Okay, so here is going to be a working version of a spin lock using these atomic primitives. Okay, so I'm going to have whatever my particular, this is going to be exchange value. So usually, your lock value is going to be something like 1. Whatever code indicates the right type of locking is going to occur. I'm going to check the memory value. Right? This is just an atomic swap here that we're going to build this around. That's actually sufficient for like 0-1 locking. Don't worry too much about it. Arbitrary amount of stuff could happen here. And then we're going to try to store the exchange value. So again, if I'm trying to use this to do a lock, right, I'm going to set this to be 1. And then I'm going to swap whatever the current value is with my 1. Now, the good news here, I'm obscuring some of the algorithmic bits. If the value was already locked and I locked it again, it's still locked, so there's no harm, no foul. Right? If the value wasn't locked and it is now locked, then I have the lock, so I'll have to check for that. Right? So there's some additional logic after this to check if the lock actually succeeded. But this at least is the atomic swap. That's the atomic portion thereof. Okay. So if anything invalidated it, this will fail. I'll notice that it failed. Go and try again. If it succeeded, right, then I'm going to keep my exchange value, and then subsequently here, I can check what the actual value was. And if this is a lock rather than just an atomic exchange, I would then jump back to the beginning again if it was in fact already locked at the beginning. Okay. Right, but there's always going to be this pattern of LL, some potential code, whatever you're doing in your critical section locally. Swap is trivial, I'm just swapping. Maybe I'm incrementing. Maybe I'm checking and modifying a value conditionally, right, what I'm doing in here. Some branch that checks whether I actually succeeded. You lose this branch, the store conditional doesn't help you. Store conditional doesn't help you if you don't check the condition. Right? And then on you go. That's actually all you need, right? So let's play this out. Okay. So let's assume that everything hits in the L1 cache. If the value could possibly be present, and let's walk through it. So let's say that here are the initial contents of our cache, right? And the initial contents, the initial contents of memory and the initial contents of a couple of registers, right? Okay. So I'm going to load T1, right? So I load into T1 here, the value from memory. I'll load a 55. So far, so good. This is going to load a 55. Still fine, right? Read sharing is okay. Now, we haven't told you exactly what coherence protocol we're using, but we're going to get some sort of invalidation-based protocol, right? So this store conditional is going to invalidate the other copy of the line, right? So when this store conditional runs on core 1, right, accessing memory location referenced by S1, we're going to invalidate this copy here. So T1 still has 55. We don't invalidate registers. We're invalidating the local cache copy, right? So that returns success, right? This is going to try to store, but it's going to fail because it was invalidated here. Right? So that's how I can run these concurrently. Now, again, you're asking, well, what if they don't interleave so nicely? What if these are both happening in the same cycle? So again, in our bus-based system, only one of these gets to the bus first, right? So even if I present core 0, I'm trying to do a store, core 1, I'm trying to do a store, there will be some winner. Will it be core 0? Will it be core 1? Will it be consistent across time? Who knows, right? It's arbitrary, right? But only one of them will pass the serialization point at a time, right? If you do not have that property, it would be very difficult to build your coherence protocol. This is piggybacking on top of your coherence protocol. Okay, so let's just skip over that. Go look at that in more detail later. It's basically just another pictorial version of what we just talked about. One more minute. I'll get this slide and then we'll switch to logistics. Okay. So if you have a cache coherent uniform memory access machine and you are using something like LLSC, then the good news on your spin locks is that they can spin on local cached copies, because the LL does not require something to become uncacheable. It does not push things all the way to the memory controller, right? It just says, timestamp my memory state here. So for CC UMA machines, or even for CC NUMA machines, one of the things that people do like about LLSC is that it is friendly in that regard, right? In particular, for a spin lock, a common pattern is I do the LL and then I check if it was unlocked before I even try to store it, right? So I can have a slightly more efficient version of my spin lock that doesn't even engage the potential write unless there's any reason to even try to, versus your other atomic primitives like compare and swap. Well, it always, right, wants to be doing that write if the comparison is there. Okay, well, test and set in particular. So the goal in all of these things is to minimize the amount of bus traffic in your bus-based system. Even if you have other flavors of system that are partitioned like a directory system, the goal will always be to minimize the amount of remote traffic in your synchronization system. Right? So the other way of looking at this is when we talked about the different design patterns. While we have lots of patterns for read sharing, lots of patterns for private data, synchronization primitives are always read-write shared. Right? If I have a lock, I am always going to be both reading and writing it, and so is everyone else. That's the whole point of a lock, right? So these are always going to be communication-intensive operations. The only thing that you can try to optimize, right, are the acquisition of an uncontested lock should be cheap, right? So if no one, in fact, actually is trying to also get this at the same time as you, it should be easy for me to get this without enormous amounts of overhead, right? In particular, if I keep getting the same lock over and over again, right, I should be able to hopefully cache some of that state, right? No one else is actually touching it. And if there are many things that are waiting for a lock, the act of waiting itself should not cause system-wide traffic. I want to be able to wait locally. Are there other fancy things you could do? Yes, there are lots and lots of types of locks. There are array locks. There are interrupt-based locks. There are proposals to do queuing on lockbit where you actually piggyback the coherence protocol to actually become an interrupt-based rather than a polling-based system. What do people still tend to use? They tend to use spin locks because they're simple, and they will work on pretty much any piece of hardware. But they are the source of a lot of overhead in real programs. And then this is also, again, sort of orthogonal to how they're actually supported. There are lots of interesting decisions on the granularity of the locks themselves. That's a parallel programming question, not a parallel processing question, right? If you write an arbitrarily bad parallel program, nothing I do in hardware is going to fix that, right? If every element of your computation requires you to acquire the same lock, congratulations on your very serial parallel program that now will actually almost certainly run much, much slower than the original, right? So, but assuming that your parallel program is well structured and optimized, right, there are some things that hardware can do to make your life easier. Again, while it's important to understand how hardware supports this, my advice for you will be the following: don't write your own locks. Do not write your own locks, do not write your own barriers, do not write your own semaphores, right? There is a reason that a bunch of people have stared at portable layers of abstraction for all of these things, whether it's POSIX, whether it's a language primitive that will work no matter where you run it, right? That understand the consistency requirements for more complex operations. So But, you know, FYI. No, God, no. No. Yeah, that's a 473 problem. That is not a. No. I want you to understand, how does an acquisition of a lock that is contended work? Writing a parallel program at this level, the most that I would ask of you is, like, you know, if I wanted to make this an atomic increment, you should be able to modify this to do atomic increment, or, you know, or if I have some sort of like a barrier pattern, we'll talk about some patterns, but yeah, you should be able to like do a few lines of assembly between these and understand how that would do a synchronization primitive. That's about. Yeah. No. Let me give you the sort of the other reason that I'm not going to bother having you do anything with that is that the simulation infrastructure that is going to accurately model how parallel program interactions actually work is well beyond the scope of this class for you to compile in practice. Gem5 is a few 100,000 lines of code, and I have found in practice that if I ask random people to just download and compile Gem5, I have a less than 100% success rate of just getting Gem5 to run, let alone having you modify it. Go find the place in the 500,000 lines of code you're supposed to modify. No. Something like Simple Scalar actually only models unicourse. So, okay. So we'll pause here on last 4 or 5 minutes of class. So given where the means and medians have been on the first 2 exams, and speaking of projects, I am going to be making mini project 2 extra credit. It's not going to be required that you do it. I will be posting both mini project 2 and the final project simultaneously tonight, so that you will have enough time to do project 3, since apparently things like project 1 took a while even. So yes. The writing assignments, writing assignment 1, I did actually finally figure out what the A-bit requirements were. So writing assignment 1 is going to go out as well, and I'm actually going to also make writing assignments 2 and 3 optional. So those apparently A-bit requirements are going to be satisfied by writing assignment 1 and the final project. So we're good there. Yeah. So there's going to be potentially 9 points of extra credit available for you if you want it. I happen to think that the papers, you should definitely go read the material for writing assignments 2 and 3, whether or not you decide to go turn them in. They are interesting. And project 2 is fun, but not strictly necessary to really fully understand what's going to go on in your final project. So let me get those out without any further delay. Design space exploration. Right. So the final project is so actually the final project is a wrapper around Simple Scalar, which has been designed to do the following. So you're going to be given a set of parameters for the costs from an energy and from latency perspectives of different hardware configurations, right? So Simple Scalar is a configurable uniprocessor simulator. You can configure properties of the pipeline. You can configure properties of the memory system. So different branch predictors, different levels of cache, different sizes of cache, different replacement policies, TLB properties, etc. And so in all, let's say, is it 13? I think we're basically exploring, I want to say it's a 13-dimensional space. I keep forgetting, might be more. Each of which has several possible configurations. So if you multiply all those out, it's a reasonably large number of particular design points. You will not be doing exhaustive search, right? And the framework that you'll be provided for the final project is designed to run a simple scalar across a set of 5 benchmarks. It's just doing a very, very short sample from all of them. Not even a representative sample really, because it's from the beginning. And it will collect that data for you. Right, so your job is to basically decide which set, using your knowledge about some of the trade-offs in performance and complexity and efficiency among some of these different design option decisions. And based on, if you so wish it, the information you are getting returned from the samples in that design space that you are executing and then collecting data from, which 1,000 points of that design space you want to sample to find the best configuration for a pair of different metrics. Right? So you're going to be given 2 different optimization metrics, and you're going to want to return 2 different points within that design space that optimize against these 2 different metrics. Right? The write-up explains all this in relatively painful detail. But yeah, it's reasonably fun. There's a framework. It is, I'll tell you this in advance, it will take a while to run 1,000 samples of 5 benchmarks by 20 million instructions each. So depending on which machine you run it on, 40 minutes an hour-ish, right? So don't try to do it the last day. Your debugging cycle might be a little longer than you desire. But there's also a write-up. So you'll pull out the data, you'll graph the sequence of metric values over time as you search through your design space. You'll write up why you have the particular selection process that you do. Right, it's fine. Yes. There you will write. Most people will write less code than Project 1. Whether it will take you more time, there are a few different variables at play there. So, but it's not that bad. Depends on how long it takes you to graph something.